So there's one thing about our universe is that, as we know, that at least what we interpret is that all velocity is relative. So Earth is rotating around the sun, so Earth is already moving. Now, if the sun is also moving in another direction, then Earth would obviously be moving along with the sun over in that direction as well. Now, this creates some interesting questions. First of all, is that given that the Earth is moving, so we know that because of our motion, Earth itself is undergoing time dilation. In addition, assuming the sun is also moving, then the sun would also be going under time dilation. Earth would be getting time dilation on top of that movement. Okay, so this raises a question. Then could there be an object in the universe that is undergoing less time dilation than we are? By definition, that object would be slower than us. Now, how would that work exactly? Well, presumably, the faster that an object is moving through space, the slower time goes for them. By that definition. See, the thing about all velocity being relative is that it doesn't take into account the fact that time dilation is different for everyone. So, if now again, if all velocity is relative, then there's no way for us to say that one object is faster than the other object. All we can say is that relative to us, we see one object being faster. So if a meteor passes us, we can say that meteor could be faster than another meteor, relative to us. But to both of those meteors, they have no concept of what's faster and what's slower. So let's look at this. Now, suppose we are an observer that's taking this picture. Again, even as an observer, we would be moving. Now, we would see that this arrow is moving faster than this one. And now, pretend these are both just rocks in space. This arrow is moving faster. But to this arrow, who is faster moving, simply sees this arrow to him, this arrow is just moving the opposite direction. So he doesn't interpret himself as moving faster than this arrow. Inversely, this arrow, to us, might be moving slower to this arrow, but to him, again, it's the same thing. All he does is that he sees that this arrow is moving away from him in space. He does not interpret either side as being faster and slower. Because again, if everything is relative, then there's no way we can say that one object is absolutely faster than the other object. Except for one problem. Time dilation. Now, if one object is indeed moving faster than another object, then that object would be undergoing more time dilation than the slower object. That gives us a way of comparing what's faster and slower. Now, if we have the ability to compare time dilation of two moving objects, then we can absolutely for certainly say one object is moving slower than another object. Now, that is an if, because we haven't actually been able to do that yet. But let's just assume that we can. Now, this would also mean that the object that's moving, that is going extreme amount of time dilation, again, time's moving very slowly for them, is moving really fast. But what's even more shocking is that if we can have an object that experiences the slowest possible time dilation, or the least amount of time dilation, by definition, their clock is moving the absolute fastest, that object will be the closest to stationary we would ever see. How does that even work? Now, the slower a clock goes, the faster that object, because the more time dilation. Inversely, the slower that object, the slower the clock goes, or the object goes, the faster their clock is moving, the slower that object. And the slower that object, be closer to stationary. Notice that no object in the universe can ever be considered completely stationary, at least not to our knowledge, except for the object with the fastest possible time. The object could be reasonably said to be the closest to stationary we're ever going to see. But again, we haven't actually seen that in real time. We haven't actually found a meteorite. Again, we haven't been able to test this, but presumably this could mean that. Now, how would that work exactly? Well, let's think about that for a moment. Now, let's suppose that one day that we come across a meteorite. Now, remember, the Earth is moving, so we are already undergoing a certain amount of time dilation. Now, we don't know how much time dilation we're undergoing, because all we can do is, say, compare other objects having time dilation versus us. For example, a satellite orbiting Earth is undergoing more time dilation than we are. But, in all realisticness, given that we know that the Earth is moving, and the sun is probably moving in a certain direction, and we have the Big Bang, we can reasonably say that the Earth is moving through space at a certain velocity. We don't know that velocity, but the fact that we have a velocity means that we're undergoing time dilation. So let's suppose one day that we come across a meteorite. Now, to us, that meteorite flying would obviously be moving. However, to the meteorite, we're the one that's moving. But what if we can measure the time on that meteor, and we find out that that meteor is traveling faster through time than we are? Now, that would be quite groundbreaking, because that would mean that that meteor is slower than us going through absolute space. They're traveling slower through space and therefore faster through time. Now, if we could do that, then that means we can absolutely say which object is slower and faster. And, more importantly, that presumably we can figure out what's an object that's closer to stationary. Now, we don't know if an object's absolutely stationary, but presumably, the slower an object goes, then the closer to stationary it would have to be. Again, it's not technically stationary. But is this test even possible? How could we do something like this? So what I propose is something like a clock test, where, again, this is still in the realm of science fiction right now. But let's suppose that we can send clocks to multiple objects. So let's suppose we put a clock here, a clock here, a clock there, and a clock there. Now, if we have different clocks everywhere, then later on, we measure those clocks, we find out which clocks are faster and slower. Now, naturally, a clock on a satellite orbiting Earth is going to move slower than us, because that object is moving faster through space, and therefore moving slower through time. But if there's a clock at the sun, or near the sun, then would that mean that that clock could be traveling faster than we are? Because they're moving less through space than the Earth is. The Earth is time dilating from our orbit around the sun. So if there's a clock at the sun, could that clock be flowing faster than ours? Again, I don't know the answer to that. And, the tech, we don't have that tech yet. But that is some food for thought of what exactly would that entail. Because right now, all we know is that undergoing time dilation, we see another clock as being slower. But theoretically, we should be able to see another clock that's also faster than us. Which, again, brings up some new questions. So, now, if we, obviously, putting clocks everywhere might trigger problems on its own. But another way of doing this is putting sort of decaying crystal everywhere, and then just figuring out when the crystal completely decays. Now, again, I'm not sure how this would work, or if this would work at all. Alternatively, what if an object is moving, having a slower orbit around the sun? How does all of these things affect time dilation? And right now, all we have known is that we've known the clocks are going slower than Earth's clock. Because, again, that's all the testing we've done so far. But, again, I emphasize that. What if we can find a clock that's somehow moving faster than the Earth's clock? Then, again, that clock would be closer to stationary in the sense that velocity might not be as completely relative as we think it is.